Okay, so the next talk is the Tradish. Oh, they're preparing. The microphone is complicated, yeah.
Yeah, yeah. I'm not last, but
okay. Book is about refinement, composition logic, and I'm just leaving the phone.
Play. Oh, sorry. Yeah. Can you hear me? Thank you. I'm Youngju, and today I'm going to talk about refinement composition logic, which is a joint work with Dongjae Lee. And let us begin with brief background. Refinement is one prominent approach in form verification. Refinement specifies an excellent end goal for the verification. For instance, consider the following refinement that for a given operating system, its binary refines its mathematical abstract specification. The refinement simply says that the source, OS spec, soundly captures all the possible behaviors of the target, OS binary. In other words, this statement ensures that the target behaves as expected, which is often more useful than ensuring just the safety. This is the reason why projects like Suricos aim for refinement as its end goal. However, establishing such an end goal in a monolithic way is quite challenging. Consequently, it is very common in refinement frameworks to decompose the end goal into smaller pieces. Shown pictorially, this is the end goal we want to prove. And in establishing this end result, we may first want to decompose it vertically. We may prove the refinement between the binary and the C implementation, and C implementation and the mathematical specification separately. Next, we may further decompose it horizontally and verify each module separately. Now, let us consider composing these refinements. If we were able to decompose the refinements as if it were cut with knives from the first place, the composition will be straightforward. However, that is not always the case. As we aim for more interesting systems involving mutual recursion or function pointers, and as we aim for larger systems that is meant to be verified with different styles of refinement, the game becomes more complex. And that is where this work comes in. At a high level, refinement-based approach comprises two verification tasks. Task 1 is to establish these small refinements, and task 2 is to compose them. There has been a plethora of work for the task 1. However, the task 2 has largely been overlooked, and this is exactly the focus of this work. The first contribution of this paper is a novel observation that common operators and their axioms in refinement framework can be soundly embedded into connectives in separation logic. In this work, we specifically focused on non-step index version of Iris, since Iris has a minimal primitive connectives in its base logic. This observation is practically useful for two reasons. The first is that it unlocks the use of tools developed in separation logic for refinement composition. Specifically, this allows us to use Iris proof mode for refinement composition, and it reduces the size of the proof by several times. The second is that this codomain is strictly richer than the original domain, and although the end goal, the larger refinement, can be already stated inside the original domain, in the proof, we can enjoy this additional structure. To summarize, the contribution 1 allows for more automated and streamlined composition proof. It does not make something that was unprovable to provable, but it makes our lives easier. Now, coming back to our embedding, there is one natural question to be raised. Can we give a model to all connectives in separation logic in terms of operators in refinement frameworks? It turns out we can do that except for this rectangular symbol called persistence modality. If a proposition P is wrapped with this persistence modality, it means that P holds, and additionally means that the proposition is duplicable. Now, the problem is that all existing refinement framework as is do not admit this persistence modality. However, I'm going to propose a novel elegant extension that can be applied to refinement frameworks in general, which makes persistence modality admissible. And this gives us a fundamentally new verification strategy. To summarize, the contribution 2 enables a fundamentally new proof strategy. To use a figure of speech, take a look at the left, and there is no way to fill the board. However, with the persistence modality, we can duplicate the block and fill the board, which was impossible before. All in all, under the guidance of this key observation around refinement composition and separation logic, this paper makes contributions 1 and 2. Specifically, these ideas are formalized by the notion of MRA. MRA is a shorthand for module and refinement algebra, comprising the operators and axioms for refinement and their composition. Then, for any given MRA, we derive the RCL. As a sanity check, we give a concrete instance of MRA and RCL, and by extending an existing refinement framework, following the aforementioned recipe. And all our results are formalized in Coq. Now let us take a brief tour of RCL. To begin with, let us have a slightly deeper look at what refinement-based verification looks like. There is a factorial module that has a single function, f, which computes the factorial of the given argument. Its implementation, tfact, is written in imperative style using recursion. And its specification, sfact, is written using direct mathematics. With this, we prove the refinement that tfact refines sfact. Then there is a main module that has a single function main. In tmain, it calls factorial twice with arguments 3 and 4 and returns their sum. In smain, it directly returns the constant 30. Now, when verifying the refinement between tmain and smain, we utilize the specification of the library sfact. That is, we prove that tmain linked together with sfact refines smain linked together with sfact. Finally, given these two refinements, we can compose them to derive the end result for this simple system. The implementation of the whole program refines the specification of the whole program. There are a number of different refinement frameworks sharing the same essence, but with different technical details, like termination sensitivity versus termination insensitivity, and small step semantics versus big step semantics. In this paper, the essence of refinement framework is captured via a common abstraction called MRA. And MRA is an algebra with two main operators, refinement and module linking. The operators should specify the axiom saying that the module linking is commutative and associative. And the refinement is reflexive, vertically composable, and horizontally composable. These are all the gold standard properties on refinement and module linking. Now, to see the contribution 1 more clearly, let us consider a program with 3 modules. Its verification is largely the same as before, except that there is just one more module. Surely, it should be straightforward to compose this refinement to yield the end result. However, as it turns out, even for this simple case, the actual proof in Coq is quite tedious. On the right is my best effort to prove the left, written in Coq. And don't try to understand the proof, it is just to give a sense of the tediousness. It comprises multiple manual rewrites of tedious axioms, especially those for commutativity and associativity. Also, when applying these tedious axioms, it is often necessary to give explicit instantiations of meta variables, which makes it even more tedious. And here comes the first key idea. The module linking operator and the refinement on the left can be embedded to separation logic using separating conjunction and update modality. Specifically, the standard axioms for module linking operator and refinement implies the axioms for separating conjunction and update modality. This looks so obvious, but to my best knowledge, this connection has not been known. And actually, when I talked about this observation, people didn't believe me until I formalized it in Coq. So the theorem on the top is the main theorem that allows us to migrate from refinement world to separation logic world. The ceiling operator simply lifts a module to a separation logic assertion, and the fact that M1 refines M2 is now represented via this update modality. Below is the rule to translate module linking operator to the separating conjunction. And again, don't try to understand this with the usual interpretation of separation logic as heap assertions. Rather, you should see it as just a syntactic formal system. And the reason why this translation works is because the axioms for refinement operators imply the axioms for separation logic connectives. For example, the axiom called update intro is implied by the reflexivity of the refinement. And the axiom called update join, saying that the update modality behaves like a monad, is implied by the vertical compositionality. Finally, the famous frame rule is implied by the horizontal compositionality. Now, coming back to the previous example, let us first embed all the refinement judgment into separation logic. Now, the composition proof of this using iris proof mode is much simpler than before. All the tedious steps involving commutativity, associativity, horizontal compositionality, etc., are automatically measured by iris proof mode. With contribution 1, we have seen why this embedding is practically useful. Let us see a more interesting benefit of this embedding with contribution 2. So far, all the separation logic assertions were just a module. But an assertion can actually be a refinement, and even more interesting ones. Let us consider a simple repeat function, which takes p, a function pointer, n, the number of times to repeat, and x, an argument. It is implemented using recursion in the programming languages like C. And I'm going to give a polymorphic specification as follows. The spec module is parameterized with fn, the function name it is meant to serve, and f, the function body. It dynamically checks whether the given function pointer is the one it is expecting, and triggers undefined behavior otherwise. If it passes the check, it uses the mathematical repeat operator to compute the result directly. With this spec module, we can establish the following refinement. And however, there is one significant issue here, that it can only serve a single client. Applying the above refinement effectively consumes the TRPT module and prevents further applications. This issue is resolved with the use of persistence modality. First, we translate this refinement into a separation logic assertion. Then, the system allows us to add a persistence modality on the right-hand side for free. Technically, any module that does not have its own encapsulated state is persistent for free. To be clear, accessing global states like memory is perfectly fine. And actually, every module written in C is persistent in our sense. Let us abbreviate the thing inside the modality as ref. Then the client of the repeat function, say foo and bar, can use this ref in their own verification. For instance, foo can refine its specification using the ref, and the client of the foo CLNT, can further refine itself using repeat applied to foo, and the same goes for the bar. All in all, this modular verification can be composed to end result as follows. One thing to note here is that the proof of foo and bar is completely modular. Foo does not know anything about bar, and bar does not know anything about foo. This is a proof that is newly enabled by persistence modality. Well, this sounds cool, but there cannot be a free lunch. There is something that needs to be extended. So in order to add this persistence modality to our system, we need an additional operator and axioms in MRA. And at the end of the day, this boils down to extending the underlying operation semantics of the module system. To cut the corners, having persistence modality allows the following judgment in the system. Note that there are two definitions of repeat function on the right-hand side. In other words, having persistence modality in the system can result in a polysemic program, meaning the programs with multiple definitions for a single name. The above judgment says that we are refining a polysemic program, but what does that even mean? If we consider operation semantics, when there is at most one function, you can just execute it. To my best knowledge, all existing frameworks give semantics to only these monosemic programs and consider polysemic programs as invalid. However, in RCL, we have to give proper operation semantics to this polysemic program. And this is not trivial, because you cannot really choose which you want to execute. And the key idea here is to use angelic non-determinism. Specifically, the recipe for extending operation semantics is whenever a function is called, angelically pick the callee to execute. It formally means to execute the intersection of all copies. And angelic non-determinism naturally extends the underlying semantics. It gives proper semantics to polysemic programs, which was considered invalid before, and does not give the semantics to semantics of monosemic programs. Also, this change is not exposed to the user. All the axioms and reasoning principles still hold true, especially the function inlining. Moreover, using angelic non-determinism here makes affinity to hold for RCL. So this is actually the most unexpected and surprising part for me in this paper. And the paper not only discusses the point I made in, I discussed today, but there are many interesting points that I don't have the time to discuss today, including our attempt to interpret common patterns in iris in the context of refinement composition, and a novel quotient tree that we used for some technical problem, and connecting MRA to iris resource algebra. Thank you for listening, and I'm happy to answer any question.
Okay. Some questions? I had a question that, so what you prove in Coq is
Yes.
the equivalence of a formalization of the refinement semantics with the iris semantics?
Yeah, we proved that, like the correspondence that I mentioned in the talk, and we also proved some examples using this newly able capability, and yeah. So if we go back to this, so if we prove the entailment in the separation logic, then that implies the refinement. So yeah, that is the main entry point and exit point for this separation logic world.
Okay, thank you. Well, let's thanks to the speaker again.